Hello, my name is Bobby Hilster and I am your particle model guru. Today we're going to talk about light and discuss whether it's a wave or a particle. Now you can pretty easily guess which direction I would go, being a particle model guru. Yeah, but in any case, it is good to go through it and see why the particle model might be a better model than the wave. So let's move on to the first slide. This is the particle model for light. It's a stream of particles moving in a straight line at or about the speed of c with a repetitive pattern. And you can see here that there are a bunch of particles here at the peak. There's very few particles in the valley, and then there's particles at the peak. The wavelength of this light is determined by the distance in meters between the two peaks. Now this particular chart was actually generated, or at least the dot part of it was generated by David using a program and using the sine wave, mathematics of the sine wave, to determine how many particles go in which spot. So this is a true pattern for a sine wave. Well, this all started back in April of 2015 when I came up with this idea, and I wrote a white paper, and that white paper is titled A Particle Theory of Light and Gravity Too. And I sent it to David, and I got no response whatsoever. I did forget to draw in a figure to have something a visual to look at, but the content was there, but David didn't say a word, didn't say anything. Well, a couple of months later, David asked me to give a presentation on gravity, and that happened on June 23rd, 2015, at what we called at that time a meetup, a local meetup. There were only three of us. David, me, and Robert Berger were there at the meeting, and I gave this presentation on gravity. After the presentation, I decided to tell David about my concept of light. Well, at that point, David goes ballistic. He's talking loud, he's waving his hands, he's on the couch, he's bent over, down, up, around, doing all kinds of crazy things. Then he gets up, he's walking around, talking more, waving his hands. And I finally get a word in. I said, Dave, this is just a model, just a model. And he turns around and he looks at me and he says, just a model? Well, things calmed down and we talked for a while, and eventually the meeting was over, and Dave and Robert were leaving. And as David was leaving at the front door, he again turns to me and he says, Dad, you know you solved the wave-particle duality. I said, I did? I had to look into it for a while in order for me to be convinced that this was some sort of important type model. But you can see that the particle model uses G1 particles, uses nucleons, G1 particles, and G2 particles. Those are the three main particles. And the G1 takes place, replaces the electron, the photon, and the graviton. In this case, we're talking about, in essence, replacing the photon. But in the particle model, light is not a wave like sound waves or water waves. For example, sound is the motion of air in wave-like patterns. An ocean wave is the motion of water in wave-like patterns. Light, as a wave, needs a medium. It needs air, it needs water, it needs something for the wave to move. Some scientists call this ether. And the particle model for light does not need a medium. G1 particles move through open space. Now here's Newton's theory of light. I got this picture from this link. You can look it up. What basically Newton said had a corpuscular theory of light. He said light was a stream of particles. He had the idea. And as you can see in the diagram, there's a blue, red, green, and yellow. And his idea was that it was the size of the particle, how big the particle was, that made the difference to your eye as to whether it was red, green, or blue. And you can see that each of these waves is actually virtually identical, has the same wave peak to peak here on these, same distribution in between. So he doesn't have this distribution that we have. And but that was his theory of light. It's Newton's theory of light. Now, people came after him, Robert Hooke, Christian Huygens, you can go on, name many, many more, Maxwell, all had this theory of light as a wave. Now, again, here we have another link to a internet source, and on the left of this picture is a particle with, that's the circle, a solid looking particle, and it has a wave drawn on it, and obviously the author of this document was trying to represent an electron. Well, there's another way that light is represented, and we call light, or visible light, an electromagnetic field. And you can see here there's a blue magnetic field which is horizontal, then there's an electric field that is vertical, and these are perpendicular to each other. And if you look at my hands, I'm going to try to get this right. Not only are the two fields vertical, but as they propagate through space, they turn and make a very complex pattern of waves. The electromagnetic field, there is what's called the electromagnetic spectrum, which goes from radio waves, which has a long wavelength, all the way up to gamma rays, which has a very short wavelength. It's called the electromagnetic spectrum. In the particle model, I would call it the G1 spectrum. But we have problems with both. Newton's particle theory could not explain diffraction, interference patterns, or polarization. The wave theory needs a medium that scientists they still call it ether. And I've heard many, many different descriptions of what ether is. At the last conference, Dave and I were the only two particle scientists there. Everyone else was an etherist explaining their form of ether and how things work. So that's not a very settled question. Well, Thomas Young in 1801, he decides to do an experiment. He devised an experiment to settle this question. Is light a wave, or is it a particle? And this is called Young's double slit experiment. Now, this video, I would like you to please look at very carefully. I want you to watch it before my next presentation. It's only 9 minutes, very interesting presentation, and he clearly, this Jim Al-Khalili, clearly talks in terms of quantum mechanics, all the particles that they talk about in quantum mechanics, and he claims that they cannot explain this experiment. So I want you to watch it, and my next video I will go over it as best I can. Now, if you go to the internet and you look up you look up double slit experiment, you'll see this key phrase: the wave nature of light causes light waves passing through two slits. That's what happens. in this theory, this model. The light is sent through two slits. My finger represent open slits through which light is sent. When you pass through, the light interferes as they go through the slits, producing bright and dark bands on the screen. A result that would not be expected if light were classical particles, as in Newton. However, light is always found to be absorbed at the screen at discrete points. They have electronic detectors on the screen, and they can monitor how light hits it, and they see little points being ping, 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 ping on that screen. And then they go through and they do a lot of other things. That's also in the video. However, such experiments demonstrate particles do not form the interference pattern if one detects which slit they pass through. That's just another part of the mess they have, and these results demonstrate the principle of wave-particle duality. They claim light is both wave and particle at the same time, although it acts as a wave at certain points and it acts like a particle at certain points. Go figure it. That's the whole point, of course. This is all about, it comes from quantum mechanics, or at least this is the nature of these experiments is described out of the what is in physics today called quantum mechanics, and they have all kinds of particles. They have leptons and all other kinds of particles with various spins and ups and downs and colors. And including in all of that is these words of entanglement, quantum entanglement, and quantum eraser, and quantum particle pairs. In terms of the pairs, these pairs they know immediately what the other particle is doing, even over large distances. Einstein called this spooky action at a distance. I'm not going to explain any of this. You want to know about all these things, go to the internet, look it up, read it for yourself. You can agree or not agree. Now, the particle model explains refraction, polarization, and diffraction and interference. Refraction I already covered. I'm going to briefly do it again, but refraction was covered in my presentation on two gravities. In fact, that's how I determined that there might be two gravities and polarization. Now, Newton's corpuscular theory could not explain these. He had a particle theory, but he could not explain them. I'm going to look at the first two. This is the figure from refraction, and I drew these force lines to say, what kind of force do I need to cause light to refract as it enters a prism? This is refraction. And what I concluded was there must be two gravities. In fact, I showed this where the G1 gravitational field around the Earth holds in the atmosphere and other loose objects, while the G2 force field around the prism is what causes light to bend as it enters a prism. The fact is the G2 force field, gravitational force field, is also around the Earth. It surrounds the Earth. And it's the cause of our blue sky because it causes refraction, and refracted light from the sun causes the particles in the atmosphere to be painted blue. And there is a G1 force field around the prism. So all objects have a force field, a G1 or G2 gravitational force field around them. Over here, the G1 force field causes the prism to fall towards the ground, while the G2 causes refraction. Polarized light. I got this diagram from this link. I have a light source, and what we have is what looks like an electromagnetic wave, because you have a horizontal wave and you have a vertical wave. Only the combination of that, what we would call electromagnetic wave, is now called unpolarized light. That's because it doesn't have one direction. As I said before, it propagates through space, twisting at the same time. So it doesn't have one direction. It has multiple directions, and as a result, they call that unpolarized light. They send that through a vertical grid, and that vertical grid literally blocks the horizontal one, leaving you with the vertical one. And in this case, it lets through the vertical one, which now is polarized. The light is now only vibrating, oscillating, whatever that means, in the vertical direction. That's polarized. That's how they explain it. Newton didn't have this concept, so he couldn't explain it. The particle model has no electromagnetic wave or polarized light. As I said before, the electromagnetic spectrum is not an electromagnetic spectrum in the particle model. It's the G1 spectrum. The particle model has what I call layered and unlayered light. This is unlayered light. Now you're going to have to think of this as streams of light coming straight at you. For example, here's all my fingers represent individual streams, and this light is coming straight at you in random patterns. Each stream is a stream of particles that has a repetitive pattern of light with a wavelength. And these are all coming at you, and this is unlayered light, and this is very much like white light, assuming that each of these patterns has a different wavelength. Okay, this is unlayered light. Now, layered light happens when you take it through these polarized lenses, and on the left you have a polarized lens that is vertical, has vertical stripes. It blocks half of the vertical ones and lets only what appears to be vertical streams of light coming at you, and so it's layered as vertical layers. If your lens has horizontal stripes, it lets through horizontal layers. Now, what you really have here is you could represent this as your three-dimensional glasses. When the camera, the projector actually, I should say, projects a light on the screen, it projects one image with horizontal layers and one image with vertical layers. Then as those layers reflect off the screen, horizontal ones will get through the horizontal, your right lens, and the vertical ones will get through the vertical lens, and your eyes will see the two specific images, and your brain makes up the 3D image. Actually, the light kind of sneaks through anyway. David and I, around Christmas of 2015, and my wife, we went to the Kennedy Space Center, and we stopped to watch a 3D video, and David did an experiment. He closed one eye and carefully watched the other one, looking for the other picture, and he claims he saw it. So it gets through, but it's a very weak signal because it was projected, for example, as horizontal, but when you look at it through vertical bars, most of it is blocked, but the image is there. It does get through, but our brain knows to figure it, to give us a 3D image. Now, the third one that he couldn't do is diffraction and interference. Diffraction is the bending of light around the corner of an object, or as it goes through a slit or the pinhole. And this will be my discussion at the next video. I ask you to remember to view this video. It's very interesting. He claims quantum mechanics cannot explain this experiment, and they're stuck with a wave-particle duality. My challenge to you is if you watched my videos, if you watched the two gravities, the particle gravity, push versus pull, particle to particle interactions, and faster than light, you should have the tools to allow you to explain an experiment using the particle model, which is what I will do the next time. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I will explain more of the universe using the particle model. Thank you for your attention.